of this workshop, so thanks for sticking around. So the final session will be lightning talks, and we have some number of speakers TBD. But our first speaker will be, so each talk we'll try to do in under 10 minutes. So in the interest of time, I will ask you to please save questions till the end, unless it's like a quick question related to like just comprehension of the slide. Yeah, so our first speaker will be Miriam, who has something exciting for us. So yeah, go ahead.
Hello, everyone. Thanks for the introduction. Yeah, I'm Miriam. I'm a PhD student at USC. And today I'm going to share our new result on obfuscation of Unitary content program. This is a joint work with Erchen, a student at UW. As Erchen has already presented a technical talk at obfuscation workshop. So today I'll take a different approach. We can consider this talk as a cute advertisement of our paper. Okay, so what is obfuscation? I guess everyone here has done some programming before, right? So usually when we look at code, we can more or less tell what's going on by just reading it. I mean just reading like the code of a program. But sometimes that's not what we want. For example, when we need to protect intellectual property, company secrets, or even something that related to national security, we don't want other people to easily understand the code. So that's where something called an obfuscation comes in. It's kind of like a compiler, but instead of just translating the code, it scrambles it and turns it into something that looks like gibberish. But the amazing thing is, even though the code looks like unintelligible, it still works exactly the same as before. So preserve the functionality. And that's basically the idea of obfuscation. Okay, so now we kind of see what obfuscation is about. Next, we might wonder what kinds of programs can actually be obfuscated. So today, I'm going to skip classical programs and only talk about content programs, since, well, that's what we are here for. Okay, so there are roughly two common types of content programs. The simplest one is just a content circuit, which has a classical description, as shown as our left-hand side. In a more general setting, a content program can also include an auxiliary content state that helps with the computation. And today, we'll only focus on the content program with auxiliary state. So good. Now we have some idea of content programs with auxiliary state. The next question would be, are we actually able to obfuscate this kind of content program? The answer is yes, we can. Bartuszek, Rakursky, Vakutanathan in Stock 24 has a result that obfuscates any content program that implements a deterministic classical function. And in this work, we show how to obfuscate any content program that implements a unitary transformation. So how to do this? Both BBV and our work need some help from a classical oracle. So let's take a look at what it can bring to the table.
Quantum obfuscation in a classical area by Miriam.
Cause the inside, logic slipping silk and right on certainly no line to trace. Only game for you, no trace. Consciousness, circuit tight, the streets not in daylight. Quantum obfuscation, can you use the new translation? Quantum obfuscation, meaning, yeah, the good target. Quantum obfuscation, negotiate, classical, okay. Quantum obfuscation,
try to break it, you're too strong. This police you'll never know. Classical mind, quantum game. You're out of sight. Sure, take the twist. No place to stand. Pull up your pant, rewind. Say you're fine. I'm gonna take you out again. What is an obfuscation? What is an obfuscation? That does it and never see it. What is an obfuscation? It gives it information. What is an obfuscation? And I might be vacant. What is an obfuscation? What is an obfuscation? What is an obfuscation? People shall I do so hard then. What is an obfuscation?
Okay, thank you. Yeah. Oh, yeah. Oh, by the way, if you like the song, you can scan the QR code here. Yeah. And I somehow forgot to put my papers link. But yeah, you can also, let me see, the number of my paper is like ePrint 2025 A91. Yeah. If you guys like the paper. Yeah. Okay.
Thanks for the great talk. Any questions? We have time for a couple. Questions can be sung also, if you desire.
Question about the video. Did you use AI to make this video? Was it an LLM generator?
So basically, I compose the song and lyrics, but like the lyrics, I actually ChatGPT for help a little bit, and then I remix the song. I ask AI to sing the song because I cannot rap. Yeah. And then they actually in like the lyrics when content obfuscation and the other ones, like you can see it, you cannot read it. So I use like different languages, so it's kind of like functionally equivalent. Yeah, but I don't know like Dutch and German, so I just add AI thing. Yeah.
So can you say like what the assumptions are for your results? So do you get obfuscation of unitaries assuming classical I/O?
So we assume classical oracle model. So this classical oracle model can be like extension by, unfortunately, BBB. And then if you want to use I/O, then like you need to use it heuristically. Yeah.
I see.
So yeah.
But that's like you don't assume anything else.
So actually, we also have like a random oracle. So if you, you use like a one-way function, then assume one-way function. But like random oracle, it's just like, yeah.
I see. Okay, thanks.
Okay, we can do one more question. If not, let's move on to the next talk. So thanks again. Stay serious. You're also from UCLA, isn't it? Okay.
That was awesome. I don't think we can talk some.
I didn't plan a prize. Okay. So next talk is by Tando and William, who are, I guess, also from UCLA.
USC.
Oh, USC.
Yeah.
USC. Okay, sorry.
We're at UCLA.
Also from universities in LA.
Yeah.
So take it away.
Yeah. Okay, thank you. Yes, so we're just going to give a very brief overview of some aspects of a paper that we're putting out in hopefully the next 2 or 3 weeks. We're focused on a reinforcement learning approach to studying entanglement and also magic dynamics in quantum systems, primarily to study things like entropy, inequality violation, and likewise. So first, just some definitional things. So entanglement entropy here, we're referring to the von Neumann entropy, which we can compute for a subsystem A as minus the trace of rho log rho. And for any bipartition of a Hilbert space into n pieces, I can always compute 2 to the n minus 1 such entanglement entropies. And of course, I could then arrange those into a 2 to the n minus 1 tuple that's known as the entropy vector. This particular construction has garnered a bunch of attention throughout the high energy literature, particularly holography, because it turns out that there are some nice classifications of states that can be derived from just the entanglement information, such as this. And so one example of that, well, the example that we all are aware of is that quantum entropy is subadditive. And so I have SA plus SB is greater than or equal to SAB. But this is a little bit boring because this is universally satisfied by any quantum system. A little more interesting is this monogamy of mutual information condition that you see in the first inequality up here, which basically tells you that if I have a collection of 3 qubits and I want to do some information processing using all of them, it's how much I can particularly do while maintaining the Bell pair connection between any pairs. But also, it turns out this is geometrically provable, famously done by Hayden and company and Hedrick, that holographic states, so any state that has a smooth classical gravity dual via ADS-CFT must satisfy this as well. And so it's kind of a quick check if you have a quantum system that you can rule out if that state has a smooth classical dual geometry or not. Sufficiently interesting, but we also would like to extend that a bit further to an inequality that's known as the Ingleton inequality, which is satisfied by all states which can be performed or prepared using linear coding schemes. And so going beyond Ingleton is essentially going beyond linear coding, and also going beyond Ingleton, because it is satisfied by all stabilizer quantum states, is a way to move beyond classicality in quantum systems. That's what we're going to focus on in this talk. And I guess for a little bit of a visual, I should also say that for any given entropy inequality, you can imagine this as some bisection of this 2 to the n minus 1 entropy vector space, where states that satisfy it live on one side and states that fail live on the other. And since I have possible qubit permutations of these inequalities, and in principle I have many inequalities that might need to be satisfied, as in the case of holographic states, I end up with this convex polyhedral region of the space in which all of the entropy vectors corresponding to the class of states I'm interested in must live. And so what we're interested in is identifying when you leave these cones, and how do you do so, and what operations instantiate that sort of transformation. I think I'm actually going to pass it to you now.
Okay. Yeah. Lovely. So now I'm going to go over the reinforcement learning technique that we're using to actually find circuits or quantum states that violate the Ingleton inequality. And so just to reiterate, the Ingleton inequality is important because it places limits on the information processing capability of our circuits, or places limits on how quickly our circuits or network, whatever you want to imagine, can be processed. And so the basic method that we're looking at here is we initialize a quantum state. For example, here I have the O+ state, and then we feed it into a reinforcement learning agent that then calculates that entropy vector that William went over, and then checks whether or not it is violating the Ingleton's inequality, and then computing a reward based on maximizing the left-hand side of the inequality, because a state would violate the inequality if the left-hand side is greater than the right-hand side. And so once it computes the reward, it picks a quantum gate operation based on which one maximizes the reward. And then it updates the circuit, and with the gate operation that was found to go closer to violation of Ingleton's. And so this is, I know it's hard for you guys to see, but this is actually the circuit that we found to be violating Ingleton's. And this is significant just because in the literature, there are like certain states that were described to violate Ingleton, but it's really awesome that we were able to find an actual circuit that could get us to an Ingleton violating state. And so this plot is just plotting out the Ingleton inequality difference as we progress through the circuit. So as we can see, the circuit is around 100 gate operations. And so when you're looking at this plot, anything that is above 0 is showing satisfaction. Anything at 0 is saturation of the inequality, and anything below is at violation. So at the end here, we can see that this is when violation actually occurs, and the left-hand side is greater than the right-hand side. And so the reinforcement learning method is helpful also because as we progress through the circuit, we can also take a look at the entanglement structure of our state. So looking to see which partitions have higher entanglement as we move through the circuit. And so this plot is showing the entanglement structure at the end, so at violation. And something that we thought was significant was that for each of the two-party regions, only the party, in order to reach violation, it seemed as if the circuit or the partition, the two-party partition on the left-hand side had to be greater than all the ones on the right-hand side. And this is something we see with this circuit, and then also a bunch of the other circuits that we found using the reinforcement learning method. And so just to briefly go over something related to the magic, just to briefly state, like non-local magic can be quantified by looking at the flatness of entanglement spectra, and we can see that, so for this plot is just kind of giving entanglement spectra of all of the bipartitions, and you can kind of see that the flatness, like not all of the regions are flat, and particularly all of the two-party regions have some sort of non-flatness or some sort of magic, except for the one on the left-hand side. Okay, and so then you can also, we had like the plots, but then you can also calculate an actual quantity to show non-flatness. So as you can see here more clearly, like CD has no anti-flatness, and therefore it's the only two-party region with no non-local magic. And so like, I know this information is not, we're not trying to say anything like concretely about all Ingleton violating states, just the ones that we saw. Yeah. And just to give a quick overview of what we've done, we were able to construct Ingleton violating circuits, found more Ingleton violating states using the reinforcement learning approach, and conducted analysis of entanglement structure and in the non-local magic. Yeah. Maybe William can hop in to talk about some things we're interested in the future.
Yeah, no, I just wanted to make the comment that, I might have turned myself off here. I just want to make the comment that one thing we didn't go over in detail is that we're all very familiar with the notion of magic in the sense of magic state distillation, where I might have some single qubit magic state, but a little less known, but sufficiently popular lately, is this idea of non-local magic, which is the magic that's stored in the entanglement structure of the state. And it was shown recently that this non-local magic is actually proportional to the anti-flatness or non-flatness of the entanglement spectrum. And that's why we are particularly studying this quantity. We are approximating it using the entanglement capacity as a measure, which gives the variance of the entanglement entropy in the entanglement spectrum. Yeah, just I guess to wrap up here, we were able to, with our combined machine learning approach, we were able to identify more states than had previously been known. To my knowledge, I thought there was only about 1 or 2 states that were known in the literature that violate Ingleton, but now we can generate arbitrary numbers of them. We can also construct circuits to get to these states from the measurement basis, and we now can study how the dynamics of entanglement and magic play a hand together when violating these entropy inequalities. And so the goal ultimately would be that when you have a classification of states that's based on one of these entropy inequalities or a collection of them, how can we see how the non-local magic and the entanglement structure actually affect these particular classes of states and help to characterize them?
Yes.
Yeah, thank you very much.
Okay, thanks. So we have maybe time for 1 or 2 questions.
Could you share what software you use for the simulations and reinforcement learning?
Yeah, so we were using PennyLane to implement our circuits, and then I programmed out the reinforcement learning agent in Python. Yeah.
Any more questions? If not, let's thank Tondo and William again. And, I think, Robin, you're next. Using the board? Okay. Thanks. Okay, so next up we have Robin Kotari from Google. So take it away.
Thanks. All right, continuing the previous theme, I also live in LA. Only allow people from LA to speak at this thing. Are you going to go next, Noah? I don't know. Yeah. It's just only LA speakers. The mic is on. That's off, yeah. All right, is that better? Okay, good. Okay, unlike the previous speakers, I don't have any fancy slides or AI-generated music videos. And also, I'm not really talking about interesting results that I have. I just wanted to popularize a question that I stumbled upon recently, and I thought maybe people would be interested in this question. So here goes. I hope no one solves it during this talk. But so the question is just the following, which is, and I'm going to give you evidence, maybe, I don't know, some background and motivation for why you might think this question is true or false. Anyway, the question is, can every n-qubit unitary be implemented in polynomial depth? But you can have exponential size. Of course, you need exponential size because, in general, to implement an n-qubit unitary, like an n-qubit unitary has like 4 to the n bits of information in it. So you'll need exponential size. But I'm saying, can you do it at polynomial depth and x size? That's okay. And also, when I say size, this includes ancillas. You might have to use. You will have to use exponentially many ancillas. Okay. So this is the question. And why might you think this is true? Okay. So one, you can do this for any classical function. So any classical Boolean function f. This is not very hard to prove, can be implemented with a polynomial depth exponential size classical circuit. In fact, you might be familiar with the result you can do with constant depth and exponential size if you have unbounded fan-in gates. But let's say we only have bounded fan-in, bounded fan-out gates. Then you need polynomial depth and exponential size. So you can do it for classical functions. So that's one piece of evidence that you might say, OK, this is good. You can also do it for arbitrary classical permutations. So I have a permutation on n bits, and this is not as straightforward. Maybe you have to think about it a little bit, but you can also do permutations with a reversible gate set. So these are the two classical analogs of this object, a unitary. So you might think, well, classically this statement is true, so maybe quantumly it's true. So that's some evidence for why you might think the statement is true. And another thing, which may not, I don't know if this is evidence or not, but we heard this problem referred to a couple of times on Tuesday, I want to say, the unitary synthesis problem, which was popularized by Scott and Cooperberg, Greg Cooperberg and Scott Aronson. And that question, I'm just going to say it very, very succinctly, which is, it essentially asks if you can implement every unitary with a polynomial-sized quantum circuit if you have access to an arbitrary Boolean oracle of your choice. And what that means is, for all unitaries, does there exist a classical oracle such that this unitary can be implemented with a polynomial-sized quantum circuit with access to this oracle? I'm just going to say it like this. This is the unitary synthesis question. If unitary synthesis is easy, like if you can do this, then this also implies this is true. So these are some, I don't know, evidence or something. These are the things I know about this problem and why you might think this is true. Before I say anything more, maybe was there a question or something? No, okay. Maybe this is a good time to take a poll. Just based on this evidence, I haven't solved the problem or anything. I'm just popularizing this question. But what do people think? Like, if you had to bet, and not one of these things where nobody raises their hand, but like if you really just had to bet, and like it's one of these things where you win money if you bet correctly, and if you lose, you don't lose anything. So there's no harm betting. Which way would you bet? But you just have to choose one of the two options. Like, do you think this can be done, or do you think it's not? It's impossible. Also, if you prove this is impossible, then this also implies the unitary synthesis is false, which is also, I guess, a long-standing open question. So, I mean, let's do a poll. What do people think? Let's first go with yes. Unitaries can be implemented in polynomial depth. Oh, we have maybe half, more than half. Okay, what about no? It cannot be done. Oh, less. Okay, good. Yeah. So, all right. So by popular vote, this answer is yes. And since I have a few more minutes, I thought I'll just tell you some. Okay, I don't know how to solve this problem, but I thought as partial progress, I can tell you some of the unitaries that you can implement in polynomial depth. And let me take this board here, which are not obvious. I mean, obviously, any unitary that's already polynomial sized, like anything that's in BQP, can be done in this. So that's kind of trivial. But let me tell you slightly more interesting things. So certainly you can do.
Do you have examples that you need exponentially many ancillars?
Yes. Yeah. You mean provably? Yeah. Because you can implement, for example. Okay. Yeah. I was going to start with that. You can make any state you feel like in polynomial depth. Like just completely arbitrary state. And of course, an arbitrary state has like 2 to the n bits of information in it, so you need exponentially many ancilla. So you can, so you can prepare ket psi for any psi of your choice. That's an example of something you can do. And because you can prepare ket psi, you can also you can reflect about ket psi. This is a unitary, yeah. So that's one class of interesting states. I already said f and pi, which is okay. Maybe I won't number these. So you can do diagonal gates. You can do permutations, as I said over there. But in fact, more generally, you can do any sparse unitary. And by sparse, I mean every row and column should have at most poly-n non-zero entries. And the reason you can do this is because we can do sparse Hamiltonian simulation efficiently. And you just simulate the Hamiltonian, which is, you just put the unitary in the Hamiltonian like this. Dagger, 0, 0. This is a Hamiltonian. If the unitary is sparse, then the Hamiltonian is sparse. And if you evolve this Hamiltonian for time pi over 2 or something, you'll essentially get the unitary that also looks like this. And then if you apply this to the state 0 ket psi, you'll get 1 u ket psi. So that gives you sparse unitaries. You can also do unitaries in the kth level of the Clifford hierarchy, where k is poly n. So kth level Clifford. And this is because the Clifford hierarchy, one of the fun facts about it is that to do any gate in the Clifford hierarchy, there's some resource state that you can be given. And then you can do the state injection protocol, and you do a measurement. And then the correction is a gate in the k minus first level of the Clifford hierarchy. So you need some resource state, but we can prepare any states from here. So you do that, and then you need to do a correction. And that correction is something, your measurement outcomes are some polynomial size string, which you will use to index these states that you need for corrections. But they're in the k minus first level. And if k is polynomial, I should say k is poly n. OK. If k is polynomial, then you only have to do this polynomially many times. And this is some interesting class of unitaries that we don't actually understand very well at all. So that's something you can do. You can do sparse unitaries. In fact, more generally, I think you can do any unitaries whose one norm is bounded by poly n, and where the one norm is not the Schatten one norm. It's the maximum absolute value of any of the sum of all the entries in any row or column. You can do this, but I think you can also do anything where this is kind of a weird norm of a unitary, where the absolute abs u is bound, spectral norm of this matrix is bounded. And let me just tell you what this is. Abs u is a unitary whose ijth entry is just the ijth entry of your unitary. Okay, I think you can do this as well. Yeah, you can do these guys, and because you can prepare stuff, you can also do unitaries of this form. J0 goes to j psi j, which is for a psi j's of your choice. Like for example, you can also do the unitary that takes j0 to j u ket j, where j is a classical basis string. And this follows from this guy over here. So this is a interesting class of unitaries that you can do. And I'm almost out of time. Let me just see if I wanted to say any other interesting unitary is possible. Oh yeah, one other thing I wanted to say is also without loss of generality, you can just assume that the unitary has plus minus 1 eigenvalues. That's because of this trick again. You can embed the unitary into this thing, and this object has plus minus 1 eigenvalues. So okay, that's some facts about this problem. Yeah, hopefully this will help somebody solve this problem. And okay, I can now take questions. Thanks.
Already saw.
Is this exact?
Oh, okay, let's say maybe my goal is just to do with constant error. I suspect if you can do it to constant error, you can just boost it to get all the way to exponentially small error. I certainly don't want it to be exact. Yeah, exponentially small error is always good enough, yeah, for me. Yeah.
If it's false, do you expect to show it unconditionally or based on some assumptions? And if it's based on assumptions, like what type of assumptions would you need?
Right.
Or could you consider?
I don't know. I haven't thought too much about how one would prove it's false, actually. Yeah, I've just kind of been thinking of what classes of unitaries you can do. With the hope that maybe if you get a rich enough class of unitaries, you can multiply them. Of course, I didn't say this, but like any unitaries that you can do from here, you can combine them, you can multiply them. Maybe you can just multiply enough and get to arbitrary unitaries. Mostly I've been thinking about the positive direction. Yeah, I don't know what you would use, but I guess you would use the kinds of assumptions that people already use for state synthesis, for the unitary synthesis conjecture, right? Like maybe you want to make some kind of complexity theoretic assumption about it. Yeah, but I don't have a good answer to this question. Oh, Daniel.
What is your vote?
Oh yeah, I think yes. Yeah, I mean, from the fact that I've been listing unitaries that I think can be done, I was just hoping that you can just keep writing down unitary classes that can be done, and eventually be like, oh, if I combine 7 unitaries from the kth level of the Clifford hierarchy with some unitaries with the one norm bounded or something, will be done. So that's why I vote for yes. Yeah.
Are there any like hard like examples of unitaries that you like explicit examples of unitaries that you think are like in this sort of intermediate range, which you don't know how to do in polydepth, but maybe.
Right, like some restricted class of unitaries or something, which is already hard. I think these unitaries are like Hadamard-like or Fourier-like, where all the entries are the same in magnitude, but the phases you don't know. Like the phases are whatever they are. I think this class of unitaries I don't know how to do in Polynomial depth. So maybe that's a hard class. Just yeah, Hadamard itself and the Fourier transform itself we can, but just unitaries that look like this. All the entries are the same in magnitude, but just have phases. I don't know how to do this.
Thanks. Do you know if you can synthesize all the examples you've given?
Oh, like in this sense?
Yeah.
Yes, yes. Yeah, I think on the algorithmic side, all the techniques we know also go to this model. Like this is a weaker model, I suppose. But I think that's true because they all rely on clever state preparations. This one relies on clever state prep. This is state prep. Sparse, yeah, this is all state prep. I think so. Yeah, I think everything is eventually boils down to interesting state preparations or reflections about states. Yeah. So I think yes, the answer is yes. I don't know any example of a state you can do here, but you can't do in this model. Although that could exist, I don't know. Maybe one could. Actually, I don't know.
All of the ones in this model can clearly be done in this model, right?
Sorry?
All of the unitaries for which you have an oracle, you can also do.
Yes, yeah. So you mean, yeah, all the unitaries that can be done this way can also be done here because, right, you just instantiate the oracle with this fact.
Okay, I think we should probably move on to the next talk, but thanks again for a great talk. Next is Andrew Gergu from IBM, who at first I thought this would break the LA streak, but then I remembered that he has lived in LA, so.
So it's like anyone who's also lived in LA counts. Yeah. What about people that have just visited LA?
I think have lived in LA would cover 100% of our speakers. So.
Is it on? Is it on now? Yes. Okay. So I also want to talk about an open problem I've been thinking about. But unlike Robin, I'd be very happy if someone just solves it right here. Okay, so the open problem is the following. So I call it the Clifford isomorphism problem. Or Clifford state isomorphism problem. And it's basically the following problem. So you're given as input the description of 2 quantum circuits, C1 and C2. These are general quantum circuits acting on n qubits. So they're not necessarily Clifford, they're just like arbitrary quantum circuits in your favorite gate set. And what you need to output is yes if there exists a Clifford unitary, let's call it D, such that this condition is satisfied. So 0n, C1 dagger D, C2 acting on all 0 is, say, greater than 2/3. So in other words, if you take the output of the 2 circuits when acting on the all 0 state, the question is asking, is there some Clifford that effectively maps from one state to the other on the all 0? And you should say no if this quantity is, say, like less than 1/3 for all Cliffords, for all. So in other words, the output of the circuits are very far from being related by any Clifford. Okay, so what I want to understand is what is the complexity of this problem? And let me tell you some facts about it first. Or maybe I should just ask if there are any questions about the problem itself. Like, is it clear what it is? Yeah.
It has to be diagonal, though, right?
What has to be diagonal? No, it's just any Clifford circuit, any Clifford unitary on n qubits.
C1 and C2 are any circuit.
Yes, C1 and C2 are any circuit. And you have like the explicit description of the circuits. Okay? So here are some facts. So one is kind of obvious, which is that, let's call this CIP, Clifford isomorphism problem. So it's contained in QCMA, because I can just give you the description of the Clifford as a witness, and then you can just check. A fact that is maybe slightly less obvious is that it's BQP hard. And the reason for this is the following. So imagine I have like any problem in BQP, like any decision problem. And let's say that that corresponds to some polynomial size circuit, which say that when the answer is yes, it outputs the all zero state. And when the answer is no, it outputs something else. So I can just modify that circuit so that in the no case, it outputs, say, a collection of magic states, like a tensor product of magic states. Okay, and then for this problem, I take C1 to be that circuit, and I take C2 to be just the identity circuit, so it just outputs all zero. So then, in the yes case, it means that there is a Clifford that can map all zero to all zero, which is just identity. And in the no case, when you're outputting the magic states, there's no Clifford circuit that would map you to a tensor product of magic states. Okay, through a slightly more involved argument, you can also show that it's contained in Q as ZK, so quantum statistical zero knowledge, and also that the complement of the problem is contained in Q as ZK. So this actually follows from like a similar strategy to the graph isomorphism, like showing graph isomorphism is in SZK, and the complement is also in SZK. And this brings me to the fourth fact, which is maybe the most interesting fact, namely that graph isomorphism can be reduced to this problem. So this problem is at least as hard as graph isomorphism. And the reason for this is the following. You could imagine that, given like two graphs, G1 and G2, I want to determine if they're isomorphic or not. So here's how I can map this to that problem. So I could start by creating the so-called graph states associated to these two graphs. So G1 is like, I take a collection of plus states, as many of them as like the number of vertices in the first graph. And then I apply a collection of CZ, like entangling controlled Z operations, between like any two plus states I and J, such that I and J is a vertex, an edge in G1. So it's contained in like the set of edges of E1, and then G2 is the same thing. And at first you might ask would these two quantum states then be related by a Clifford? And the answer is always yes, because they're just stabilizer states. So you need to transform these states in such a way that they're related by a Clifford when the graphs are isomorphic, and they're not related by a Clifford when the graphs are not isomorphic. And the way you do that is you just apply a tensor product of a Haar random unitary on top of G1 and G2. So like you take the same Haar random unitary, you apply it on both of them. And the claim now is that if the graphs are isomorphic, then the only Clifford that can map this state to this state is like the permutation, like the sequence of swaps that implements the isomorphism. And if they're not isomorphic, then there will be, like you can show that there will be no Clifford that can map from one to the other. So, like some things that we don't know that I think would be interesting to show is like, can you show that like this Clifford isomorphism problem, that you could solve it in BQP with an oracle for graph isomorphism? Or, is it even just in BQP proper, which would mean we could solve graph isomorphism quantumly in polynomial time? That's maybe more unlikely. But yeah, there are other facts you can show. So if one of the circuits is just identity, then this just becomes stabilizer testing, and this we can do efficiently in BQP. If you ask the analogous question with polys instead of Cliffords, then again, you can solve it in BQP. So there's like a hidden subgroup algorithm that can solve it in that case. But for the Clifford case, we just don't know more than this. At least I don't know more than this stuff. Yeah, that's basically it.
Thanks. Questions?
Are you willing to make any conjectures?
Yeah, I don't know. Like, I'd be willing to conjecture that this is true, like that there's a reduction, like a quantum reduction to graph isomorphism. But yeah, I'm not, like I wouldn't bet too much money on that.
Okay, maybe this is a little too like inside baseball, but I remember when you last showed me this reduction, I was like kind of skeptical because like graph states can sometimes have this property that they're sort of like locally equivalent to another graph state that looks different, and maybe it's not isomorphic. Have you rigorously shown this fact, or is it just like probably works out?
Yeah, it's more in the probably works out category. This was Adam Bullen's idea, so I'll just blame him if it's not true.
Okay.
But yeah, it seems like it's probably true, but okay, one would have to show it rigorously.
Other questions?
You said if you replace the Cliffords with Pauli's, then this problem becomes solvable.
Yeah.
Have you tried any other things easier than Cliffords? Like for example, like C0 circuits or something, which is like a special case of Cliffords. But
right. So if this is like any unitary that squares to identity, then you can just solve it quantumly, efficiently. It basically becomes a version of Simon's problem whenever this is the case. Yeah, it's maybe not too clear why, but if like I denote this thing as like psi2 and this one as psi1, then given these two circuits, I can create the state 1 over root 2 like 0 psi 0 plus 1 psi 1. And the point is that if there is a like a unitary that squares to identity that maps one to the other, then this is like a coset state for the hidden group. Let's call it like X and whatever that unitary is. Let's say U. Right, and then you can just solve it like Simon's problem, more or less. Yeah.
So we know that wait, let me just get you the mic.
So we know that graph isomorphism is in co-AM. Do we also know like something similar with like CIP being in like, I don't know, like what are the equivalent quantum class?
Yeah, I don't know like anything other than this thing. So there's like, I guess QSZK is 2 round. So there's always a 2 round protocol for it. Yeah. For it and its complement.
Any last question? Okay, if not, let's thank Andrew again and maybe move on. So I think you two are the last 2 speakers. Do you have a preference which one goes first? Or okay, so continuing the theme of people solving problems posed by Andrew, we will have Noah Shadi from Google telling us about something that we might remember from Tuesday.
Robbie's talk is going to be more inspirational. Mine is kind of depressing a little bit because, yeah, on Tuesday, Andrew. You have to turn on the. Does it work now? Okay. Yeah, Andrew in joint work with Sergei Bravi and who else was it? Kriston Temik had this idea for a problem that a quantum computer could solve, but a classical computer could not. And the nice thing about this problem is that it's verifiable, so classically, and could be used to prove that you have a quantum computer. And the other nice thing is that it was like in really low depth circuit land, so maybe we could do it in the near term. But then we kind of were talking about it, and it seems like maybe there's a bit of a letdown classically that it might not be actually that hard. And the reason is not maybe what you might expect. So the way that Andrew's problem, et al.'s problem worked is that you first make a function f, which is a low-degree polynomial that's a sum of several low-degree polynomials, f1 through fn over k, where k is some constant. And you have some variables, x1 through xn, and x, so the first polynomial only depends on the first k variables, and so on. So they just depend on these like little chunks, right? So this is like a very special kind of polynomial where you could make it in a way that guarantees it has a large autocorrelation. So f hat f would be large, 1, say, or -1. And the point is that you could test this with a quantum computer, but you can also figure out that autocorrelation just by looking at f because of its structure, because it's local. And so instead of sending the quantum adversary that you're trying, the prover, instead of sending them f, you would generate g, which is, so g of x is equal to f of a times x, where a is a random orthogonal transformation over f2 to the n. And what they proved is that for orthogonal transformations, this g has the same autocorrelation, so it's not changed. But on the other hand, this would totally sort of scramble up what the polynomial is. So this g might look super random and not local at all. There wouldn't be a clear partition into these terms. And the degree, though, would be constant, or sorry, it would be the same as before. So if this is, say, a cubic, this would remain a cubic or a quartic or whatever. It would never change. So you could maybe think about it and see if you can figure out how to actually de-obfuscate this while I erase this. And does anyone see right away like what the method is, or if you don't already know? Okay, so this is a super important family of methods to watch out for. And I will just say that all of these fall under the sort of general header of Grosvenor basis methods. And so the real thing you have to do in practice is you generate specific instances, give them to a computer with optimized Grosvenor basis software, and just see if it works. But I'll just give you some intuition as to like why they will be able to solve this problem. So given this function g, right, we can sample random x in 0, 1 to the n as many times as we like, and then evaluate g of x. Right, it's just going to be some bit in 0, 1. And then say, well, this has to be equal to f1 plus ... plus fn over k of a times x, right, for some unknown a. Right? And we know what x is. That's just bits. So we can express this as a linear combination of terms like f1, ijk, right, where this is the coefficient in front of the term xi, xj, xk in f1, right, times a I prime, a j, j prime, a k, k prime, times this value x I prime, x j prime, x k prime. So it's kind of notationally verbose, but the point is this is just a bit that we know because we sampled x in the first place. So instead of the variable being x, the variables are now the coefficients in this nice decomposition, as well as the orthogonal transformation matrix elements. And these are now just a bunch of polynomial equations over F2. But now the variables, again, are these unknowns. And crucially, we're using the fact that there's this nice decomposition that exists, and it's just our job to find it. So now we can do this many times. So we get an equation, say 1, through an equation big N, and then we just have to solve it. And the question is, when will we be able to probably recover from those equations the unique solution, F1 through Fn over k, and the entries of the matrix A? And the answer is there actually isn't a unique solution, because there are many local orthogonal transformations that will just leave this decomposition invariant. But that's kind of a subtlety, and you can sort of overcome that in various ways in practice by, for example, pinning random bits of the solution to random values until there's like one unique solution that's left. So I'm just going to ignore that and pretend there is one unique solution. So when would we expect to find it? Okay, this is kind of fun. So what we do with these equations, you can think about what happens to them as like we have a bit, right? G of x is, let's just say 1, and then that's equal to f1, 2, 3, 4, et cetera, plus a bunch of other terms, right? So we take each of these monomials, say a12, a34, a56 times this thing, right? And we take each distinct monomial and we promote it to its own variable. So we'll just call that big fancy Y sub f1, 2, 3, 4, a1, 2, a34, a56. So it's like notationally terrible, but we're only going to get a polynomial number of distinct monomials. So we're going to end up with a linearized system. That's what they call this, a linearized system where the solution would induce a linearized solution in terms of these curly y's, in some arbitrary monomial ordering. And once we have enough polynomial equations over here, then the matrix we get will become taller than it is wide. And at that point, if you assume that these rows were kind of random, then you would expect a unique solution. And that's the point where these Grosvenor basis methods really start to work in polynomial time. So naively, what will that be? Right, so on the right side is going to be your g of x bits. So that's going to be, so how many monomials do you have? Right? Here we have how many f's? It's an arbitrary cubic, so that's like n cubed f's. And then the number of entries of A is n squared, so the number of triples is like n squared cubed. So overall the number of monomials is like, what is this? O of n to the 3 plus 6. So it's at most, n to the 9th power, right? And when we linearize, right, we need at least this many equations, right? Because at that point there's going to be a unique solution. So we need n to the 9th rows of our matrix. But we can sample polynomially many bit strings x and plug in and get an equation. So this is polynomial time. And then we run Gaussian elimination, which is like cubic time. So sort of naively, this will take time into the 27th, which is kind of a joke, right? But in practice, Grosvenor basis software is really nice, and it doesn't literally just do this. This is kind of just a way to think about when the techniques will start to work. So this is pretty unfortunate, and one observation is that if this had worked, you could actually use a very similar idea to obfuscate a Simons-like oracle, so a periodic oracle, where you would take a periodic function of x1 through x, say k, and then you would send instead g of ax, where a is now some sort of long and short matrix, or oops, the other way around. Yeah. Sorry, g. So I would send g equals f of ax. That's right. So now f this structure means that g is periodic. So if it were difficult to recover this affine transformation, it would be difficult to de-obfuscate Simon's oracle. So yeah, we were talking about maybe ways of getting around this and fixing the proposal. maybe by adding noise to the equations, and then you get something maybe kind of like LWE. But yeah, these methods are super important to be aware of, and I wish they didn't work, but they do, so sadly. Actually, they're kind of cool, but yeah. Yes. There was
a question down there.
Curious, do you have an estimate?
Let me give you those
like what the Grosvenor basis method scaling would be in practice?
So the question is what the Grosvenor basis methods would scale like in practice. What do I estimate? Yeah, I can't really say. I've read some papers about this, and I don't understand them. They rely on the degree of semi-regularity of the polynomial system, and it's kind of hard. But I have run software. I can recommend im4GB. It's not very user-friendly, but it works. It's like the fastest I've found that's open source. If you are willing to pay for software, I think Maple and other programs have it. But anyway, I can't really give you a good. That's like why you really need to pick a particular problem size, and then you just say, attack this.
But I guess you'll know when you get the right answer with Grosvenor basis.
You'll know when you get the right answer. Yeah.
Test empirically.
That's right.
All right. Thanks.
Sort of related to that, do you expect that it might be better than n to the 9?
Oh, yeah.
Okay.
Yes, because you're not going to get all monomials, and you could start to make as you know, you could try and put A into some normal form where many of the entries would be 0. So there may be ways of really hacking this, but yeah, this matrix shouldn't actually show up in your computation.
Can you say in 3 sentences what the Grosvenor basis methods do as a black box? Do they solve exactly?
Yes, I can. The way that I think about them is they, in effect, are creating this big matrix with each monomial being promoted to its own free variable. And then on top of that, they add all these extra rows which correspond to facts like, obviously x, y is, what is it, x times y, z is equal to x, y times z, right? But you can very this fact as a linear equation and then make this matrix even bigger. Also, this matrix is very sparse, so you don't need to, you shouldn't just create it in memory. So, but yeah, if you want a more formal introduction to Grosvenor bases.
Maybe I can rephrase. Let's say I had a black box API call to Grosvenor basis methods. I guess what they're doing is you have a polynomial and it looks a certain way, then it's solving for that polynomial.
Oh yeah, you're saying what do you give it? Yeah, so Grosvenor basis methods are a little bit, I think of them like SAT solvers for algebraic problems. But of course they're very different from SAT solvers. But the input is going to be so any polynomial f1 of x1 through xn through, say, f capital N of x1 through xn. These are just some polynomials. And you say, find me a Grosvenor basis for this algebraic variety. So if there's a unique solution, then it will actually find you x1 through xn. Or it will tell you, it can tell you if there are no solutions. If there are many solutions, it will characterize for you what all of those solutions are.
So regarding adding noise to the equations, I was also thinking about this during the talk, but I somehow convinced myself that would also make it harder to solve quantumly. So did you think of any way to get around this?
Yes, we've thought about this a lot actually. So, and me and Andrew and maybe others have had a similar idea, which is instead of adding noise over f2 adjoint x, right? So instead of adding a polynomial over f2 adjoint x, imagine if we were over the reals, right, somehow, and we had generalized like correlation to be over the reals or something, then maybe we would start with f of x equals f1 plus f n over k. And then we would get g of x equals f of ax. And then this is going to have a large autocorrelation. And then we would send g twiddle, which is g of x plus epsilon times h of x, where this is like a small constant, right? Then if this is really small, then it's close. So maybe the autocorrelation is still big, whatever that means when you generalize. And in practice, what you might consider doing is working over fp, where p is like, a million or something. And then at that point, it kind of behaves like the reals in terms of the noise robustness, but all of the numbers in G could still be really big, so that there's lots of wrapping around, and you can't just use like linear least squares to overcome the noise classically using this algebraic attack. But then, like as Andrew pointed out, at this point it becomes very similar to LWE, and it seems less near-term NISC fault tolerant, early fault tolerant. But maybe you have like other ideas, or yeah.
I mean, if you can try and add quantum noise and see what that does to the equations, maybe there's some way of like using some like basic error correction methods to overcome it. Yeah, I don't know.
Cool. Okay, maybe we should move on to the next talk. So let's thank Noah again. So I think last is Robbie King from, wait, what's your current affiliation again? Okay, so you were saying you were unemployed earlier. Oh yes, okay. So Robbie King, independent researcher. But eventually at Simons,
That's right.
Okay, eventually at Simons will be telling us something inspirational. So.
I don't think your mic's.
Do you want to just change your mic?
No, his.
Oh, mine was on. Oh.
Because they couldn't hear it.
Oh.
Is this working? Yeah.
Okay.
Okay, so I guess a few months ago now, I was invited to contribute a blog post to this blog at Caltech run by John Preskill and Spiros. And it's called Quantum Frontiers, if you want to check it out. And yeah, so I did that, and the theme was about quantum algorithms research. And if you sort of glance at the blog post, it's very sort of hyped up, and like in the kind of way that all of you are probably allergic to. So, but there is really sort of an idea in there that I thought quite hard about. There's sort of in that you have to go through all of the hype and get to the middle of it to find the idea. But I thought I would just sort of say it here, just to this audience. So, okay. So, okay, I guess a good entry point might be to think about this sort of direction that I guess Scott Aronson has been proposing a lot, which is to find a classically verifiable task that we can run in near term. He has this Venn diagram. And I'm going to sort of put forward that maybe that raises a sort of a bit of a false dichotomy. So you can think of it as like, what are the different hierarchies of what we might want from something with quantum advantage? So I'd say right at the bottom, as everyone would probably agree, is random circuit sampling. Right, that's sort of the most useless possible thing you could do with a quantum computer. Okay, and then right at the top would be something that's, I guess, classically verifiable. Okay, so over here I'll put like examples. And I'll write examples, but to be honest, I think I'll end up putting all of the examples on the board because there's really not too many. So here, there's actually many examples of, generically, you can get hard sampling tasks everywhere in physics, right? If you just pick any sort of Hamiltonian and any initial state you evolve in, you try and sample, that's going to be classically hard. So this is sort of, it's very easy to get difficult, classically difficult sampling tasks. Okay, classically verifiable, we have Shor's algorithm. We also have this OPI problem that is solved by DQI. And I guess we also have these sort of these planted quartic speedups as well, but that's not, those are quartic, not exponential speedups. But I guess those belong in the classically verifiable. Okay, but we sort of think of this dichotomy, and here's the point I want to make. The point is that I think the whole game is actually in between these two. I actually think the whole world of useful quantum computations might be sort of not, not RCS, but not classically verifiable. So what goes in the middle here, right? So if I'm like wondering if my new quantum algorithm is useful, how do I sort of have a filter that I can pass it through and say, do I believe that it's going to be useful? And so what I thought very hard about is what to put as a criterion for what should go in this middle section. And what I landed on is, there's two ways of describing it. One would be, you could say it's quantumly verifiable. Another way to put it is that it's repeatable. Okay, what do I mean by this? So my claim is that all of physics simulation, all of chemistry, all of physics, all of those applications, right, the applications that we think of as like the main ones of quantum computing that are going to be useful, land in this middle category. So what's an example? Suppose I prepare some interesting quantum state on my quantum computer and I measure its like magnetization or something, and I get 0.3 magnetization. Right? I can't verify that efficiently. I just measured 0.3. But what do I mean by quantumly verifiable? I mean that if I run that quantum algorithm on a superconducting quantum computer and at the same time on a neutral atom quantum computer, and they both give 0.3, then the physics community is like, okay, I think the answer is 0.3. Right? So it's sort of like that is proof that you've reached out into nature and brought back with your computation a fact of the matter. Right? In the same way, suppose you sort of, with your quantum computer, you predict that some material is going to have some super cool property, and then you go into a lab and you fabricate it, and you get this material, and then you sort of are testing it, and indeed it does sort of function as a solar panel or a superconductor or something. That's a verification, but that's actually a quantum verification because nature is quantum. Okay. So when people get confused about this, for example, like, I asked Thomas Vidic what he thought, and he sort of was like, why are you trying to verify BQP with BQP? That's sort of trivial. And, that's true, but I think the fact that, but it's not the fact that you want to do that, it's just the fact that that's possible, I think, is a pretty good proxy for, this middle sort of layer of utility. Okay, and so I guess what I'm advocating for is that we should be looking for stuff in here. And I think, okay, again, so in a few weeks I'll be starting a part-time role at Google, and so I'm such a loyal and good employee that I'm already advertising their work. But I do think that this OTOC sort of project by Google does land in this middle section. Another one I think is also by Anthony at the back of the room there. His paper on sparse random Hamiltonians from a few years ago, I think, is also a candidate. But there's not too many, and Of course, things get put here and then they get broken, so then they get taken off the list. And I think this is, the current list, but, Okay, so I'm just going to say maybe one more thing, which is to write down okay, the sort of how should we make progress? Okay, so this is the challenge to quantum algorithms researchers. Okay, find a quantum algorithm plus, let's say a distribution over inputs, and we could call this a problem such that, number one, the quantum algorithm works, so provable correctness of the quantum algorithm. We would like that because we don't have quantum computers, so we'd like to make sure that the proposal is actually provable. Okay. Second is so provable correctness is, in fact, let me just try and be more consistent here. So let's say this first one is really about quantum easiness, right? So here we want provably correct. So classical hardness. Do we need provable classical hardness? Well, we can't even prove that Shor's algorithm is hard. So let's just relax on that one, right? Like, we don't need some sort of query lower bound. Let's just say no known algorithms achieve this task. And that one is like, it's your responsibility to really try. You can't just put out random stuff. You have to that's going to be 90% of the work, actually, is coding stuff and looking at all the different algorithms, seeing if they're going to work. So this is really the, that's you have to be honest. Okay. And the third is this thing here. Verifiable, or, okay, let's give this one a title. The title here is potential utility. And then here we want verifiable, or at least repeatable. And that repeatable would be this middle ground. Okay, so that's, I think, my humble opinion of the correct direction for quantum algorithms. Now let me just say a few more things before I finish. So you could say, okay, what about all of these algorithms, frameworks that we've shown are BQP complete or something? Where do those fail? Well, those fail because they don't actually specify a problem. What you've done there is you've translated quantum computation into a new language, but you haven't actually found a specific algorithm and a specific problem. Okay, what about these oracle separations? Well, the problem with the oracle separations is, again, okay, so if you instantiate the oracle in a silly way, probably you'll lose the classical hardness, right? And so the task is to actually find an instantiation of these oracles. Okay, but the last thing I'll say is more hopeful, which is that we're told from our friends in physics and chemistry that really physics and chemistry is not solved, right? There are things out there that we see that we don't know how to predict, with classical methods. So really this challenge should be achievable if we believe them about that. So, okay, I'll finish there. Yeah, thanks so much.
Thanks for the talk. I actually would like to ask a question. Do you think maybe things from high energy physics could fit in here? Say in lattice QCD, they're always trying to calculate the mass of the proton from first principles or whatever. That feels like you can go check it against an actual proton, and I don't know. Do you think that would fit in here?
Right. Okay. So another thing you could see even simpler is why don't I just pick a strongly correlated molecule that they don't know the ground energy or something like that. channel. Okay, so the problem with those, this is also a problem like why can't you just say, figure out the phase diagram of the Fermi-Hubbard model or something. Okay, the reason why those don't actually work is because those are not actually problems in the sense that they're not classically hard because they are very small data. It's just like the phase diagram of a Fermi-Hubbard model is some function on 2 variables or something that is, you could solve it with a lookup table. I guess the complexity theoretic language for that would be like p/poly maybe? Is that right? It's like solvable in p/poly. So we really want a problem where like, you know, it's a distribution over an exponentially large space of things. Each one, I sample a new one every day, and it's always going to be unpredictable, and we need the quantum computer. And the reason why we'd like that is because we would like evidence that the sort of demand for quantum computation is going to be indefinite, right? Suppose there's only 5 questions out there that we need the quantum computer for, and we sort of run them all on the first day. That's not sort of
the
most exciting.
You've done the neutron. I mean,
yeah, yeah. So I guess that's. Yes,
do you think similar statements? I mean, what's a similar problem in classical case? I mean, just ignore all the quantum parts. You just say like, in the classical world, I want to, for example, 100 years ago or many years ago, people like when the classical computer is not that good, and people ask, okay, we want to demonstrate the power of those computers. Like, I mean, is there any similar results in classical case? So I mean, I'm just trying to understand when you say like, I mean, when propose something different than a specific, for example, say a specific Hamiltonian. So I'm trying to understand this, like, what's the, ideal results?
Right, maybe there is no analog because I guess what we're really asking is like, what is classically complex about quantum physics? So
you mean like a model which captures sound?
Yes,
taking
that's right. So an answer to this would be exciting because it would have some sort of feature that you could then study, right? It would be like, it would have like a sign problem, or it would have like something you could then sort of get your hands on and look at, and that's where the complexity is sort of coming from.
So is this thing on? The issue with
totally dead. No, we can try the other one. This one's working.
So the issue with using BQP complete problems is just that it's difficult to generate instances that are not just classically easy, right? Like with k-fold correlation, if I just sample the functions at random, the correlation is likely just going to be 0.
That's right. That's right. Okay. So yeah, thanks for the question. So I think if you have a quantum algorithm and you show it's BQP complete, I think you've almost proven that you haven't addressed this question. It's almost like a proof that you haven't done anything. You know, I don't want to be like too mean, but like, because okay, so like, you know, what does that tell you? It tells you that I can take any of these and embed it into my problem. So I could do that with Shor's algorithm. I could solve Shor's algorithm with this thing. But you're right. What is the issue with, say, picking a random instance? Now, what generally tends to happen, so suppose we're in this sort of, in this world, the physics world, where we're sort of trying to compute a number, right? Where like we pick a random, what's an example of a BQP complete problem? Okay, like let's take correlation, for example, right? Okay, so I pick 2 random functions, and I ask about the correlation. What's going to happen generically is that the answer, the number that you get, will concentrate over the inputs. And so what an experimentalist would say is there's no signal, right? So the signal is exponentially small. There's nothing you can do on the quantum computer in that case. So, and I think, to be honest, that is actually where 95+% of the attempts actually fall down. So I think if you get past that hurdle, if you find a distribution where you have a signal, you should start getting excited. That's actually a pretty good sign.
That's exactly the problem of random circuit sampling, right? Like,
yes,
the value in a quantum circuit is like
right.
making it complete.
Yeah, all the observables will concentrate. Actually, that's right.
We have a lot of questions.
I guess I'm curious why you think that quantum verifiability is like the right thing to look at in terms of making our life easier. Just because, like, from I guess a structural point of view, to me, it doesn't necessarily guarantee that that part of BQP has like something I can hold on to. So, especially compared to classical verifiability, like I don't immediately see an advantage besides that we know of some problems that have this property.
So this axis is sort of a increasing potential for utility axis. So, if something is classically verifiable, then it's sort of definitely potentially useful. But I would say something is already potentially useful if it's verifiable, quantumly verifiable. I guess the final answer to that is that nature is quantum, so that's the quantum verifier. That's a very abstract answer, but
isn't everything quantumly verified?
Not random circuit sampling.
Okay.
Like random circuit sampling, I have the same random circuit. I run it one day, I get a bag of strings, and I run the same circuit on the same computer the next day, and I get a different bag of strings. Yeah.
Okay, yeah, I just wanted to ask what you think about, for example, potentially adding a fourth thing, which is like the question of like how easy it is to sample problems from your distribution. In particular, for example, Scott, has talked about this idea of like peak quantum circuits, which generally aren't easy to find, but perhaps if there's like some nice way of finding them, they could be a nice way of doing, verifiable quantum advantage. And in particular, whether there might be another thing in that middle area there, which is like things that are like quantumly easy to generate, even if they're classically not easy to generate. Like maybe there's, some problems where there's some quantum algorithm for actually coming up with the instances.
Yeah, those are good points. I haven't actually thought about those. I guess implicitly here I'm imagining the distribution is something you can sort of write down. It's not some like implicitly defined thing that you need to. But you're saying what if what if the distribution, what if the problem you can only sample the input using a quantum computer in the first place?
Yeah, efficiently, maybe, yeah.
Is there an exact, it's like...
Well, so one, I don't know if this is actually possible, but one could imagine that maybe you could use a quantum computer to do some sort of optimization to come up with peaked quantum circuits in a way that's much more efficient than trying to do the optimization on a classical computer.
Yeah. Okay, I'll think about it. I don't
Just thought it was, maybe interesting.
It's interesting.
Yeah, so I think I just want to cycle back to Jiaqing's problem. So I think, if you want like a classical problem that somehow roughly matches this, but all classical would be, you can have like spin glass problem, average case, people think they're just really, really hard, kind of know what they're doing, and you can propose your favorite generic solver, right? Give you like belief propagation or simulated annealing, and people do indeed they do this and they can prove a lot of things. So like, that sounds to be like an example of people, something that would fit that challenge, or do you
spin glasses? Yeah, but there's no.
Yeah, I'm saying though, so the classical version, in order to say a classical computer is useful or an
you're answering Jiaqing's question.
This is try to answer that question, or I can see whether you agree with that. Sort of, this will be a template.
Yeah, for sure. That is a finding a low temperature string of a spin glass would have definitely 0, 2, and 3. It's definitely a well-defined distribution, right? I sort of sample a random instance. Definitely, it's we don't know how to solve them, and if we could solve them, then it could be potentially useful for optimization, right? What's missing out of the spin glasses is the quantum easiness.
Okay. So I think that sort of brings to a question because people study spin glass not necessarily that it really capture the structure we see in real world, right? So maybe this is go back to the question of how do you pick the ensemble? Because like sometimes when you pick this ensemble, they're sort of being picked so that you can analyze it as a theorist.
Yes.
So then if you're just already real-world instances that you just throw it and you see, oh, it works, like simulating annealing often just works, then somehow, you can revisit again whether it's worth sort of trying to.
So the question is, what good does a model that satisfies these requirements do when we can just wait till we have quantum computers and then go out and solve actual problems?
Yeah, this is sort of the,
so I would say two things to that. I would say, first of all, I think that a model would potentially give us a better understanding of where to look in the real world for like quantum advantages. Like if it has some features or something, you can understand like where is the classical complexity coming from, and then you could sort of find places in the real world that have those features. That's the first one. The second one is that if you found a really clean model and really good example, and it was condensed and really like all of the quantum easiness and classical hardness was really like packed in there, it would potentially be the first thing that we could run that would demonstrate quantum advantage. It would potentially be like the cheapest thing as well. So those are my two answers.
Hi. Yeah, this is sort of related to the previous questions, but the key reason why your challenge is hard is because you want this distribution over problems, right? Over exponentially many problems. And is that really necessary? Is that really what we want? I feel like in physics, we really have finitely many questions that we care about, and there are only finitely many molecules that are actually interesting. Like maybe this whole thing of trying to define an asymptotic family of problems is just not the right thing to look at.
It's not the right thing because maybe it doesn't exist and that's okay, or
it doesn't exist in physics, it seems to me.
But if there was such a thing, wouldn't it sort of improve your belief in the utility of quantum computers?
It would, but maybe it's not necessary. Like just, figuring out the phase diagram of Fermi-Hubbard model, or like.
Yeah. I'm not denying those things are going to be very, scientifically useful and impactful, and those things will happen. But I think, to be honest, those things will happen whether or not, what we do as theorists in this room. So I think, yeah.
Sorry. Okay, we can take one more question. Wait, Matt, did you already ask the question, or I'm simplifying? Previous talk. Okay, well then you can.
I mean, okay, Noah's question was probably good too, but it seems to me this repeatability thing is the thing that to me is unfamiliar, as compared to like complexity theory, where the other ones. But for repeatability, what you're talking about with repeatability, doesn't this mean that we need a computational model that's not the standard gate model, not Hamiltonian complexity, because you're saying like we're going to run this on two different hardwares, and we want to know if it's consistent. And if we model them both with the same model, then our theory is going to say that it will be consistent, or just identical mathematically.
Yeah, I think this might be the same confusion that Thomas Vidic was having.
Right. Yeah. Exactly. Right, it's like
you're asking
BQP is BQP.
Yeah. What's the point? What's the point of verifying it? Right. It's like.
Well, no. I think what I'm asking is, if you want us to use a different computational model, then a physicist should tell us which one it is.
Even you run it on the same computer the next day, actually.
Oh, okay. That counts as repeatability.
Yes. Ramstorm doesn't have that.
Okay. All right. Then I'm fine with it. Yeah.
Yeah. I mean, I'm not saying it's like you would actually want to do that, but you maybe actually would want to do that, right? Like if that would be more sort of if they did run the same model on two different quantum computers and got the same answer, that would be pretty compelling to, I think.
Well, you gave that as an example at the beginning. That's why.
I'm just saying that the repeatability is sort of just a mental tool to help you think about, like, are we actually predicting something about nature or about the...
I can think about it with the same quantum computer, just running it the second time. Is that okay?
Yeah, that's fine. Yeah.
Then it resolves it. Thanks.
Could I answer the question that maybe make Matt a little happier? Just
like the first thing is like the class BQP intersect NP, and the second thing is FBQP, and the third thing is SAMP BQP. He's just saying your problem should be an FBQP. Right.
Yeah,
It doesn't need to be BQP intersect NP. That's okay.
He gave this example at the beginning of the talk where he said like you compare, you run it on one hardware and you compare it with another.
Right, but I guess he's just trying to say like the output should be a number. Like it shouldn't be a distribution, because then if you do it again, you get a different answer. It should be one number.
Yeah. This is fine as a definition.
Yeah.
Okay.
Okay, I think we were told to end at 5 sharp, so I think we have to cut off the questions here. But thanks everyone for staying till the end. And I just want to thank again all the speakers in the lightning session, and also all the speakers in the workshop as a whole, and my co-organizers and the Simons Institute staff for helping us out with this great workshop. So thanks and safe travels.